In the last class, we were discussing about the micro machining, and we started with the very important micro machining process that is known as electron beam micro machining. I had shown you the setup for electron beam micro machining, as you can see here, and we have already discussed while we were discussing the electron beam micro machining section. So, various elements are shown here. You can clearly see the workpiece where electrons are hitting and raising the temperature of a local area to a very high value, such that it melts and vaporizes the material to be machined in case of metals. Now, electron beam machining is mostly done in the vacuum atmosphere for the very simple reason I will show you. Suppose vacuum is there, you will get, as shown in this particular figure, a very fine machining. As you can see, the beam is coming straight and hitting the workpiece, and the scattering of the electrons from that particular direction is very minimal, although some is there. Now, if you are going to use the atmospheric air in the machining zone, then what will happen? That many of the electrons will strike with the molecules of the air, and they will get scattered, and you will not get a good cutting. As you can see over here, that is electrons are scattered all around, and you are not getting a straight beam as before they start hitting the molecules of the air, and you will not get as good cut as in the left hand side, where vacuum is there in the machining chamber. So, although there are some configurations, some systems of electron beam machining where vacuum, high vacuum is not created, they are able to machine it. That time they need very high energy for the electron beam to overcome the scattering to some extent due to the collision with the molecules of the air. Now, I will show you something very important applications in case of micro machining area of the electron beam micro machining process. Here you can see the pattern of the holes drilled with the help of the electron beam machining process. These pattern of the holes are very important in some of the industries, namely food industries, where juice etc. of the various fruits or cereals are prepared, and you need very fine holes through which these juice are filtered. Especially in case of textile industries also, you need very fine holes of the filter, and that too made on the non corrosive hard strong materials. Here you can see that hole size is 90 micrometer and holes density is 4000 holes per square centimeter, which is a very high density, and the workpiece of the material is stainless steel, and the thickness of the workpiece is 0.2 millimeter, that is 200 microns, and total time taken is very small, 10 microsecond per hole. But the industry people, some of the industry people are not satisfied with this size of the holes, they want still smaller holes. So, they have used electron beam machining process again, and they are able to create 6 micron size holes at a very high density of the holes per unit area. You can see 200,000 holes per square centimeter they have been able to create in the sheet of just 120 micron size, and the time taken has substantially reduced compared to 90 micron size holes, and here the time taken is 2 microsecond per hole. So, you can see a very specific applications of electron beam micro machining, especially in creating the patterns or circular patterns or the holes in the stainless steel sheets, which are used for filter for making the filters. Let us see some specific important applications of laser beam micromachining. Laser, full form of laser is light amplification by stimulated emission of radiation. We have already studied this. In this case, light energy of a particular frequency can be used to stimulate the electrons in an atom to emit additional light with exactly the same characteristics as the original stimulating light source, and photon energy is proportional to frequency, but inversely proportional to the wavelength, and the photon stimulates the atom, causing it to emit an additional photon with identical characteristics to the stimulating photon. So, this is a chain reaction and you have large number of photons in the area where you are producing the laser beam, and there are 3 types of the lasers: gas laser, liquid laser, solid lasers. Here 2 are shown here, written here. Gas lasers are CO2 gas lasers, and which has 10 micron as the wavelength, and excimer laser which have 193 to 351 nanometer as the wavelength, which is smaller than CO2 laser, and solid state lasers, namely very famous laser, that is the Nd:YAG laser, which has got 1.064 micrometer as the wavelength. Now, when you are using the long pulse laser beam for micromachining purposes, there are certain problems which have been observed as very clearly shown in this particular figure. You can see the surface debris in large number at the top surface being machined, and then you can see here damage caused to the adjacent surface. Here it is the adjacent surface, where here is the hole being machined. So, in the adjacent surface some damage is caused. Surface ripples due to the shock wave can be seen over here, and recast layer, which is the property characteristic, undesirable characteristic or property of all thermal machining processes. So, here also you get what is known as recast layer, which is clearly seen. Apart from that, you can clearly see here micro cracks are there, and heat conduction is definitely there, which raises the temperature gradient inside the workpiece. So, these are some of the defects which are really not good as long as machined hole or machined material is concerned. They are not desirable. So, these are the demerits. Now, if we go for a short pulse laser micromachining, whatever disadvantages or demerits we saw in case of long pulse laser beam machining, they are not seen over here. You can see that there is no damage caused to the adjacent structure over here. Second thing, ultra fast laser pulses are shown over here. So, you can clearly see the difference in the short pulse and long pulse lasers. Now, there is no recast layer seen over here, and no melt zone is visible, no micro cracks are there, and heat affected zone is also not shown over here, and there is no damage, no surface debris on the top of the surface or machined surface. So, these are some of the characteristics of short pulse laser machining. So, we can conclude that short pulse laser beam micromachining gives better surface characteristics after machining as compared to long pulse laser beam micromachining. We all know already that 2 types of lasers are there. One is the continuous wave laser and another is the pulsed laser. So, we are talking of the applications of pulsed lasers. So, there are hardly any merits of short pulse laser shown over here. Property of the process and process characteristics of laser beam micromachining. Mechanism of material removal remains the same as in case of macromachining, that is the melting and vaporization. Medium in case of laser beam micromachining is normal atmosphere, it does not require any vacuum in the machining zone as in case of electron beam micromachining. Tool is high power laser beam, and maximum material removal rate which researchers and industrialists have observed is very small, 5 millimeter per minute. Specific power consumption is 1000 watts per cubic millimeter per minute. Critical parameters are beam power intensity, beam diameter and melting temperature of the workpiece material. Materials applications, you can apply it for all materials, it may be electrically conducting, electrically non conducting, magnetic, non magnetic, metals or non metals, but laser beam micromachining is not good for those materials which have high reflectivity, such as copper. It is not good for copper and aluminum, because copper has high thermal conductivity also. So, limitations are, as you can see here, very high power consumption, cannot cut materials with a high heat conductivity and reflectivity. That is why I mentioned aluminum and copper. Let us see some other property, other type of the lasers. There are two other types of the lasers known as picosecond lasers and microsecond laser. Now, wavelength in case of picosecond laser is 532 nanometer to 355 nanometer, and for microsecond lasers it is Nd:YAG laser, which I have already mentioned, 1064 nanometer. In case of minimum spot diameter, it is 1 micron in case of picosecond and around 45 micron in case of microsecond lasers. Vertical wall machine capability, aspect ratio of 2 and aspect ratio of 2 in case of microsecond laser as well. Now, traveled wall machine capability, aspect ratio of approximately 5 to 10 in both the cases. Deep hole drilling, accuracy of workpiece motion is plus minus 2 micron in case of picosecond laser, machining accuracy plus minus 1 micron in case of picosecond and plus minus 20 micron in case of microsecond laser. Average power of laser is about 10 watts in case of picosecond laser and 100 watts in case of microsecond laser, and materials machine, metal, ceramics, polymers, glasses etc. in case of picosecond laser, metal, ceramics, opaque glass etc. in case of microsecond laser. Now, let us see very specific applications of laser beam micromachining. You can see here in this figure micro cutting in a tungsten pin using 511 nanometer Nd:YAG laser. This is the micro cutting and it is a tungsten pin. Here you can see the microfluidic device in silicon showing laser drilled hole and connecting channel. Here you can see the laser drilled hole and this is the connecting channel, and you can see the scale over here for 50 micrometer, and you can imagine the size of this hole and the connecting channel. Connecting channel is smaller than 50 micrometer as is clearly visible from there, and the references are given over here. Now, here is very interesting applications of laser beam micromachining, specifically excimer laser. Now, you know in the hair it is very difficult to write anything on the hair, because if you try to write it with the help of the thermal process, it will burn immediately. You cannot apply mechanical process for micromachining, and also you cannot apply electrochemical or chemical process. However, researchers have used excimer laser for writing excimer laser word on the hair, and you can see clearly shown over here they have written excimer laser, and this is the zoomed view of the word excimer, and you can see the scale over there, and this is very clearly visible. So, it is really surprising that researchers are able to write on hair the word excimer and laser, and they are very clearly visible over there. Micro machined letters on a single human hair. Note the clarity of the letters in the close up view. Here is the close up view. Electrochemical micro machining. Now, this setup we have already discussed while we were discussing electrochemical machining in our earlier chapters, and this is quite obvious, where you have the tool as the cathode and workpiece as the anode, and electrolyte is flowing between the gap or in the gap between the two electrodes. Now, there are, this is for macro electrochemical machining, but for micro electrochemical machining you have to lower down the voltage which you are using over here, and this is the setup shown over here developed for electrochemical micro machining by Bhattacharya et al. At Jadavpur University. Now, these are the basic reactions that take place when dissolution of the anode, that is the workpiece, takes place. You get ferrous hydroxide plus hydrogen as the gas, and in some cases in place of ferrous hydroxide you also get ferric hydroxide depending upon the machining conditions. And here ferrous or ferric is decided by the valency at which the anode material is dissolving, because iron can dissolve at more than one valency, either 2 or 3. That is why you are getting ferrous hydroxide or ferric hydroxide, which we have already discussed in case of macro machining. So, you have to scale down the machining parameter, you have to reduce the size of the tool depending upon what you want in the workpiece. Here is some comparison between the electrochemical machining and electrochemical micro machining as long as machining parameters are concerned. The voltage that is taken normally is less than 10 volt in case of electrochemical micro machining, while in case of electrochemical machining you use 10 to 30 volt. The current in case of micro machining is less than 1 ampere, while in case of macro machining you can go as high as 40,000 amperes. Some industry people have used 40,000 ampere as the current. Current density in case of electrochemical micro machining is very high, 75 to 100 ampere per centimeter square, and in case of macro machining it is 20 to 200 ampere per centimeter square. Now, in both the cases you can use continuous DC or pulse DC. Frequency is in terms of kilohertz in electrochemical machining, that is macro machining, and it may be as high as megahertz in case of micro machining. Electrolyte flow rate is quite low in case of micro machining, that is normally less than 3 meter per second, while it is quite high in case of macro machining 10 to 60 meter per second. Electrolyte, you can use various kind of the electrolyte in both the cases, whether macro machining or micro machining. Electrolyte temperature does not go very high in both the cases, normally it is between within 60-65 degree centigrade. However, theoretically you can go as high as 90-95 degree centigrade below the boiling temperature of the solvent, that is the water in normal cases. Electrolyte concentration is normally kept less than 20 gram 20% in case of micro machining. Size of the tool is large to medium, while in case of micro machining definitely is a micro size tool, and inter electrode gap is very small in micro machining, that is 5 to 50 micrometer, and this is micrometer, and you can use the operation as a mask operation or maskless operation in case of micro machining, and machining rate in case of micro machining is 5 micrometer per minute or so. These are certain figures, but they will vary depending upon what parameters you are choosing. Then accuracy you can get plus minus 0.02 to 0.1 millimeter, and surface finish is very good in case of micro machining, as you can see, as good as 0.05 to 0.4 micrometer, and feed rate is quite low. So, one has to be very careful in selecting the machining parameters in case of electrochemical micro machining, otherwise your workpiece may get damaged if you do not properly select the machining parameters. Let us see some of the applications of electrochemical micro machining. Here you can see an example of 3D electrochemical micro machining, where you can see the portion has been milled and some projections are there. So, copper structure, a small prism 5 micrometer by 10 micrometer by 12 micrometer machined into the copper sheet of an electronic circuit board. Now, you can see the scale also given over here for 30 micrometer. So, the sizes of different parts or sections of this cavity and projection can be evaluated. Now, here is the titanium surface microstructure made by through mask electro micro machining, and scale is given over there. If we see the enlarged view of one of the cavity, you can see so nicely made cavity over there, hemispherical kind of the cavities that are shown here, although they are not hemispherical, but very smooth cavities are produced with the help of this particular process. So, a smooth surface and sharp borders that are achieved under optimized dissolution conditions, that can be clearly seen over here. This is another application, production of high accuracy holes. You can see the size of the holes, scale is given at the bottom, and micro holes produced on a alloy cylinder using jet electro micro machining. Now, there is another very important process in case of micro machining or nano machining is concerned, and that process is known as ion beam machining. Here actually the beauty of this process is you are removing the material atom by atom. So, sputtering off or knocking out atoms from the workpiece surface by the kinetic momentum transfer from incident ion to target atoms. Now, we can see here this is the incident ion which is hitting the top surface of the workpiece. Ideally, it should hit the atom over here and remove one atom as shown over there, and the ion itself strikes it and goes away. But normally this does not happen, because this is happens when low energy of the ion is there, and this is an ideal case. But what really happens in actual practice is like this, that the ion has enough large energy and it does not remove one single atom, but a cascade of atoms are removed from the top surface of the workpiece, and if the energy is very large of that particular ion, then it gets implanted in the subsurface of the workpiece, and this is what exactly we do not want, because it damages the surface of the workpiece being machined. So, removal of atoms occurs when the actual energy transferred exceeds the usual binding energy of the atom with reference to the surrounding atoms. At sufficiently high energy, the cascading events will penetrate more deeply into the solid. Several atoms or molecules will be ejected out, and the bombarding ion will become implanted deep within the material, as you can see over here. So, this is not the desirable feature. You can see over here that FIB alone ion milling, you can get this kind of the surface, FIV with the gases, you can get enhanced etching like this, ion implantation may take place like this, selective etching can be done like this, and ion deposition. Now, another beauty of this particular process is that it is not only for removal of the material, this particular process can also be used for deposition of the material. So, ions of different materials, although selected very limited one, they can be deposited on the top surface and you can use it for generation of the micro or nano features. As you can see here, these are the nano features which have been developed or produced by deposition of the material. So, this is the beauty of this particular process, that you can use it for both purposes, additive process or attrition process, where material is being removed or material is being deposited. Now, these are some of the examples of the products that have been produced at IIT Kanpur. Now, you can see here some of them have been produced at IIT Kanpur. These are the different features of the spring that have been built using focused ion beam setup, and this is another one, bent hollow tube of silicon oxide whose outer diameter is 4.8 micron, height is 14.5 micron, and lower part constructed by depositing and conjugative rings translated with respect to the previous one. So, you are depositing it and moving upward and you are able to create it. Upper part constructed with one deposition with continuous translation of the ion beam, this is the upper part, and this is very interesting, such a micro products have been developed. Now, this is the another example not done at IIT Kanpur, elsewhere, micro electrochemical cell fabricated by ion beam deposition of platinum. Note the horizontal branch connecting the inner and outer electrodes. You can see this is the inner electrode, this is the outer electrode, and this is the horizontal branch which is connecting the two, and this gives you the scale. So, these are some of the very interesting, peculiar, real micro products which have been produced using the focused ion beam process. Now, this table is very interesting to understand the limitation of focused ion beam machining, because this cannot be used, this process cannot be used for large amount of material removal. As you can see here, that the material, various materials are given here and removal rate are given here in terms of micrometer per hour. That means, you can remove a layer of 2 micron in 1 hour from the quartz. The large maximum amount of material can be removed from the silver, that is the 3 micron per hour, and in other cases it is just 1 micron per hour. So, this the kind of material you can remove is very small. So, you have to be very careful that you do not intend to remove comparatively larger amount of material. The material being removed should be somewhere in nanometer range rather than even many micrometer range, otherwise it is going to take very long time. So, thank you very much. Thank you.